All right, let's do an example of finding maxes and mins by hand. So we'll use x cubed minus x squared minus 2x on the interval -1 to 3. Remember, we're calling the left end of the interval a and the right end of the interval b. So step 0, do not graph. Remember, the point of this is to practice our skills in finding mins and maxes using by hand derivatives. We will graph later to check stuff, but for now we won't. Step 1, take the formula-based derivative. So f prime of x, what's the derivative of x cubed minus x squared minus 2x? You get 3x squared minus 2x minus 2. Step 2, set that formula equal to 0. So we'll say 3x squared minus 2x minus 2 equals 0 at which x values? Can you think how would you solve this kind of by hand? Well, actually, before we do that, we should go type our formula-based derivative into Desmos, and also have Desmos graph f prime. Make sure the two match. You can trust me that here they do, or you can verify it's just a polynomial. How do we compute where this happens? Remember, we're trying to find the x where this happens, not just set x equal to 0. To solve this, you need the quadratic formula. So you'd say -2 plus or minus the square root of -2 squared minus 4 times this times that. So 4 times 3 times -2 all over 2 times that leading coefficient. So you get x equals -0.548-ish, and x equals positive 1.215-ish. All right, step 3, where is f prime non-existent? And this is just a quadratic function. It exists everywhere. It's nice and smooth. Step 4, compute the y values at the x values we just got. So f of -0.548 is whatever. F of 1.215 is whatever. Oh, I got it here. 0.631, -2.11. Step 5, check the endpoints. F of -1 is 0. F of 3 is whatever. I don't feel like plugging it in right now. We'll take a look at it on Desmos later. And then step 6, of all those y values, the highest and the lowest are the global max and min. Here it wouldn't be a bad idea to make a table. So at -1 we had a value of 0. At -0.548 we had 0.631. At 1.215 we had -2.11. And at 3 we had whatever. So which is the smallest of all these? This one ends up being large positive. So this is the smallest, so that's the global min on the interval -1 to 3. This one ends up being the global max. We'll fill that in a sec. What about this one? That's where the derivative is 0. Why is that not a global max or global min? Well, let's go take a look at it. Step 7 is graph it to check. So let's switch to Desmos. All right, here we are in Desmos. So here's our original function, which we haven't graphed, but now it doesn't hurt to graph it. Here's the by hand derivative. We can show that, and here's the Desmos f prime derivative. So we can check. We probably did this checking these two against each other back when we were doing the derivative by hand. Here I've entered the quadratic formula. I gave the answer to this one, I named it c sub 1. The answer to this one, I named it c sub 2. Then in Desmos, you can make a table like this. If you go to the plus and say insert a table, and you can type in x values. So we know the left hand of the interval is -1, the right hand is 3, and the other points I care about in the interval are those. And if you click this, it'll show you those points. So that was a 12. We can go back and fill that in our table. So we had said that this was the global min on the interval, that one right there. And that does indeed look to be the lowest point from -1 to +3. And we had said that this one was the global max, which is true. What about this one, which is where the derivative is 0? How come that didn't end up being a local max, max or min? Well, it is a local max, but it's not a global max. And this procedure, it finds candidate points and then just judges them based on their overall y value, and it doesn't look about what's happening nearby or not. So it can't be too certain about whether something is a local max or min. All right, so that's our first example.